In today's video, we talk about how to derive a Poisson distribution. So the first part is to introduce some basic facts about Poisson random variable. But the main purpose of this sequence of videos is to derive the property mass function of a Poisson distribution. So that is the chance that a Poisson random variable x equal to a lowercase x is equal to e to the lambda and then times lambda to the power x and over x factorial. We want to derive this formula in several cases. The first case is that we are assuming that we observe a random variable in a Poisson process that satisfies so-called the Poisson prostitute. And under this condition, we want to show three proof of this property mass function. The first method is to use the linear differential equation and then the mathematical induction. And the second method is to use the characteristic function. And the third method is to use the moment generating function. Also, in the part C, we want to show the Poisson distribution is a limit of the binomial distributions. So which means that the Poisson lambda is about equal to a binomial with number of try equal to n and probability of getting success is equal to lambda over n. We still want to use the moment generating function to show this fact. In part D, we derive the Poisson random variable from a sequence of RID, exponential, inter-arrival times. In the last part, we derive the property mass function of Poisson in non-homogeneous Poisson process. So that's our plan. So let's move on. So we will introduce some basic facts about Poisson distribution. A Poisson random variable actually assumes non-negative integer values like 0, 1, 2, 3, da da da. Unlike the binomial random variable case, for Poisson random variable, there's no finite upper bound. And people use Poisson random variable to model the count data in the real data analysis. Well, we write Poisson random variable as this. So Poisson tilde and then Poisson and then a number lambda. And lambda is the parameter of a Poisson random variable. And the possible lambda value is all non-negative real numbers. So this lambda actually can be thought as the name of a Poisson random variable. So actually, lambda is equal to the expectation of the Poisson random variable. Here's a simple example. So suppose that number of phone calls received at CAT's help desk at Rice State University, say between 8 and also 8:10, may follow a Poisson distribution. And also based on the past experience, suppose that average number of calls received in this time period is equal to 5. So we may ask, what's the chance that more than 6 calls will be received in the next day between 8 and also 8:10 in the morning? So here we write x is Poisson, 5. So the lambda value here is equal to 5. And we need to find the property that x is larger than 6. So that is the property x larger than 6 is equal to the sum of the property that x equal to lowercase x when this lowercase x running from 7 and then to infinity. In most of the statistics textbook, the property mass function of Poisson random variable actually is given directly without explanation. So we always see that the chance that a Poisson property mass function is equal to this form. So it's equal to e to the negative lambda and then times lambda to the power x and over x factorial. And for x equal to 0 and then 1 up to whatever infinity. And also for a fixed number, lambda is larger than or equal to 0. So people may ask, where does this property mass function come from? So in the following videos, we provide three scenarios that generate this property mass function, so which should provide a solid foundation for the Poisson distribution. There's a special case for this lambda value. So if this lambda value equal to 0, and then the random variable actually reduced to a constant, x equal to 0. For any other lambda value, and then x assume each value from 0, 1, 2, 3, and with a certain positive properties. So here's one simple example for calculation. So we want to compute the chance that x equal to 7. So in this case, the formula is e to the negative lambda and then lambda to the power x and over x factorial. So in this case, the x value is equal to 7 and then lambda value is equal to 5. So applying this formula, we have this expression. So e to the negative 5 and then 5 to the power 7 over 7 factorial. So this is about equal to 10%. And if we want to calculate the property that x larger than 6, and then this will be the sum of the property mass function running from x equal to 7 and then to infinity. So these are there are infinite many numbers in this summation. But this is also equal to 1 minus the chance that x equal to lowercase x, but when this lowercase x running from 0 to 6. So we can apply this formula like for 7 times here, and then we finished calculation is about equal to 24%. These two calculations can be viewed in this property bar graph. So what does the property bar graph is that we list the possible value for the random variable x. So in this case, x assuming 0 and then 1 and 2 and da da da. And also we list the property mass function. So that is the p of 0 in the first spot, and then p of 1 and then da 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 da. Okay, so this bar is the chance that x equals 0. So the height of this bar is just equal to the chance that x equals 0. And then if we want to calculate the property x equal to 7, and then we locate the number 7, which is here. And then the height of this bar, this will be equal to the property that x equal to 7. And if we want to calculate the property x is larger than 6, so this means that we're starting from x equal to 7, and then 8, and then 9, and then da da da. And then we want to add up all the height of these bars together. And then that will give us this value here. There's a special property for Poisson random variable, which says that the mean and also the variance of Poisson are identical. So that is the mean of x is here, and then equal to lambda, actually it's also equal to the variance of x. So for example, we want to see why this is the case. So we just follow the definition of the expectation, so which is equal to the value of x and then times the property mass function here. And then since when x equals 0 and then the first term is equal to 0, so we change this lower bound to x equal to 1, and then we apply this transformation y equal to x minus 1, and then this summation change to y starting from 0 and then infinity. And also we can pull the common lambda out, also this e to the negative lambda out. And if you look at this summation, and this is simply equal to e to the lambda. So if you multiply these three numbers together, and then you can see this is equal to lambda. You can also show the fact that lambda equal to the variance of x in this way, but it will be more complicated. Follow the property number 5. We can see whether a dataset comes from a Poisson distribution in the following way. So from the dataset x1 through xn, and we just calculate two numbers. One is the sample mean, the other one is the sample variance. So for example, our sample is like the first value x1 equal to 38, and x2 equal to 42, and up to whatever, the last observation equal to 38. And then we compute the sample mean, which is the sum of all of these values, and then divided by the sample size. So we have this 38.55. Also, we can calculate the sample variance using this formula here. And then we find out that this is equal to 29.62. So if you compare these two numbers, and then you can see that there's a big difference between these two numbers. So which were indicating that the sample of x underscore will not come from a Poisson distribution. For a random variable x, and there's an associate important function called the characteristic function. So it's called the phi sub x of t. And for the Poisson case, the characteristic function is equal to e to the lambda, then times e to the it, and minus 1. So in this case, the value of this I is equal to the square root of negative 1. So the characteristic function actually is a complex function. So to see this fact, we can see that the characteristic function is defined as expectation of e to the I times t times x. So this is equal to the summation of this function value, and then this part is the property mass function. So just plug in this value, and then we find out that we can combine this term e to the itx and with lambda to the power x as this form. And then you can see the sum is simply equal to e to the lambda times e to the it. So you will combine these two numbers together, and then we got this result. So in this derivation, we use the fact that e to the a is equal to the sum of a to the power of x and over x factorial for any value of a, which is in the complex plane. There's another important function called the moment generating function, which is the MGF. So for the Poisson case, the MGF is equal to e to the lambda times e to the t and minus 1. We can derive this fact here. So the moment generating function actually is equal to the expectation of e to the t times x. So it's equal to e to the tx and then times the property mass function. And then again, you combine e to the tx and with this lambda x as e to the t times lambda and then to the power x. So this is equal to e to the lambda times e to the t minus 1. These two functions actually will be used to derive the Poisson distribution later. The moment generating function actually can be used to find the moments of the random variable. So for example, you want to calculate the first moment, e to the expectation of x. So this will be equal to the moment general function, and then we take the derivative, and then we evaluate at t equal to 0. So which means that we want to take the derivative of this function, which is this part, and then we plug in t equal to 0, and then we got this lambda. So this result actually is consistent with our result here. And also, we can calculate the second moment of Poisson random variable like this. So which means that we take the second derivative of the moment general function, and then we evaluate at t equal to 0. So which is equal to lambda squared plus lambda. And based on these two facts, we can compute the variance of Poisson as the second moment and then minus the square of the first moment, and then we obtained equal to lambda. And here we want to spend a little time on characteristic function, also the moment general function. The characteristic function defined as expectation of e to the itx. This function actually always exists for any distribution, also for any real number t. This is because that the function e to the itx is always bounded. The moment general function, however, is equal to expectation of e to the tx. This function does not always exist. For Poisson random variable, for normal random variable, for binomial random variable, the moment general function exists. But for Cauchy distribution, the moment general function does not exist. The reason is that the e to the reason the moment general function may not exist is that the e to the t times x may be very large if the x value is large. So we say that the moment general function exists if it is finite when t belongs to an open interval contain 0. You may notice that the moment general function at 0 is always equal to 1. For two random variables x and y, and we can check when they have the same distribution by checking that whether their moment general function are identical. So this means that x equal to y in distribution if and only if they have the same characteristic function. So phi x t is equal to phi y t. A similar property holds for moment general function as well. So suppose that the moment general function for x and y exists. Okay, so this is the condition. And then x equal to y in distribution if and only if their moment general function are identical, like this. Next, suppose that we have a sequence of random variable xn, and each with a moment general function. Each with a characteristic function, and also we have another random variable x with the moment general function like this. And then, if the limit of this if the limit of this characteristic function here converges to the characteristic function of x, and then xn will converge to x in distribution, also vice versa. And similarly, suppose that xn has a moment general function, and then if the moment general function of xn converges to the moment general function of x in the neighborhood of 0, that is, for this t belongs to negative delta for some positive delta value, and then xn will converge to x in distribution, also vice versa. So why are these facts important? A Poisson random variable actually can be viewed as the limit of a sequence of random variable xn. So we can use the fact 2,1, also 3,1 to prove the part B2, and also use the fact 2,2 and also 3,2 to prove the part B3 and also C, also D, also E. And this fact 2,2 will be used to prove the part D in the next several videos. So this is the end of video 1, and we will derive the property mass function of Poisson. So we want to derive this formula under 5 different methods in the next 5 videos. Thank you for watching. See you later.